All right, so the last presentation will be given by Zhiyuan Chen from Princeton on high-rank finite generation via the Rees construction. Please go ahead.
So the higher rank finite generation problem very generally is the following. So let X be a projective variety and let L be a Cartier divisor. Then we can consider the section ring of L. This ring has been studied a lot, so let's maybe assume this is finitely generated. So let V be a real valuation on X. Then the vanishing order of V induces filtrations on this ring R. And we have an associated graded algebra, GRVR. So the most general question maybe one can ask is, when is this graded ring finitely generated? So not much is known in this generality, and why do we consider this problem? The main motivation and the main known cases come from the case stability. So now we assume X is a KLT final variety. And L is the anti-canonical divisor, or multiple such that it is Cartier. Then Liu and Zhuang proved the following. So if we compute the delta invariant, compute the delta invariant of X, and in the case it is smaller than or equal to 1, then GRVR is finitely generated. And there is a local analog of this problem. So we see X is now it's affine, and we consider a KLT singularity. And then Zhuang proved the following. So if V is also computes a similar invariance, it's a minimizer of the so-called normalized volume. Then now we don't have a ring, a section ring, but we can consider the graded ring on A. Then GRVA is finitely generated. So in both cases, this valuation are actually good in the sense that V is quasi-monomial. And more importantly, it is an LC place of a Q complement. So this means that there exists some gamma Q linear equivalent to Kx. The effective X gamma is log canonical, and the log discrepancy is 0. So the problem is that, however, if the rational rank of V is larger than 1, which do appear in these two cases above, then this condition LC place of a Q complement is not sufficient for finite generation. So maybe a more precise question we can ask is what geometric condition implies finite generation in addition to this LC place? So the work Liu Xizhuang and Xizhuang mentioned above, they used something called a special complement. And I will come back to this later. And I want to introduce my main theory, which is the following. So we consider a slightly different situation, and I will explain it after I state the main theory. So we have a pair YD, a log canonical pair. And a polymorphism such that minus ky minus d is ample. And assume some condition on singularity. So we write the coefficient one part of d as some ei. And assume every LC center of YD is contained in E. And every EI is Q cartier at these LC centers. Or maybe at the generic points of the LC centers. And another assumption is that assume the intersection of this EI is irreducible. Then we have finite generation for the valuations way inside. Let me write as QMZ circ YE, and I will explain that later. And we can consider general ring. So L1, LS be Q cartier divisors. R is a box ring. Then GRVR is finitely generated. So let me explain that by some remarks. So first, this ring R itself is finitely generated because Y is of KLT phenotype over spec A. So R itself is finitely generated by MMP by BCA Chen. And two, what does this mean? So under the conditions that every EI is Q cartier at the LC centers, so YE is actually locally at the generic point of Z is the quotient of an SNC pair. So this is follows by a lemma in vernacular and where they define QDLT are exactly this kind of things. Then, so we can talk about monomial valuations at this point. And they are given by our real numbers. And the three is that if the pair YD is DLT, then these conditions are both. So LC centers are just a strata of E in this case. And this essentially we recover the previous known results of XZ and XZ. So this is equivalent to their special condition on valuations when YD is DLT. But actually, our results applies to more valuations than in the DLT case. Maybe let me give some examples. So first, maybe it's not so interesting, but we can consider divisorial case. Let's say we have more valuations. The X is S, and we apply it to sorry. So we are in the affine case. So if E is a divisor over X, and it's an LC place of a Q complement. Then by BCHM, we can extract this divisor E on a birational model such that minus E is F ample. Then our theorem also includes this case, but E is special if and only if it is a polar component, which means that the pair YE is PLT. And we do know there are more LC places of Q complements that are not polar components. And maybe a more interesting example is in higher rank. Now we consider a simple funnel. So it's a smooth funnel hypersurface of degree D in Pn. And we consider two hyperplane sections. And we may assume they are also smooth. Then this thing minus kx plus E1 plus E2 is ample if D is less than D n minus 1. And let D be the E1 intersects E2. So if E is integral, then at the generic point, this pair is X E1, E2 is SNC, so we have valuations. And if so, maybe let me see. Z is actually a hypersurface in Pn minus 1 of degree D. And if Z is KLT, then XE is, sorry, if Z is integral here. Then the pair XE is DLT. And if Z is only LC, then our theorem applies. But the previous theorem of Liu-Zhiyuan only applies in the DLT case. And now maybe let's see what is the ring, just the coordinate ring of X. Then what is the graded algebra? If you take the approach, then the graded algebra is just a comb over Z. So the next part is, how do we see what is this graded algebra? That is theorem 2. So with the same assumptions, each EI gives a filtration Fi on the ring R, and we can form the Rees algebra. Which is just Fi and I, and T minus L. So this is a subring of R T1 TR, and it's an algebra over the polynomial ring KT1 TR. So theorem 2 says the following. So first, the extended Rees algebra is flat over the polynomial ring. And the second, the central fiber Rees quotient by T1 TR. Maybe let's call it R bar. So R bar is an integral domain. And then these two actually, they imply that the graded ring of V is actually isomorphic to R bar. And we know that Rees algebra is finitely generated also by BCHM since we are on a chaotic funnel. So this R bar is finitely generated. So this is how I can prove theorem 1. And finally, we also have a corollary. So we can say that R and or maybe the Rees algebra and the R bar are graded by NS, which are S different line bundles, and R, which are this EI induces grading. Then the weight cone of R bar, which are generated by in which degrees R bar is non-zero, can be described as following: is then by or M or NM such that Z is not contained in the stable base locals of some NILI minus some IEI. Okay, so that's what I want to talk about.
Thanks so much. Any questions? Actually, I have one question. Is it possible to say one word about what's involved in the proof of theorem 2?
Oh, yeah. So we want to study flatness, and we want to consider structuring. So we consider the complex. And this is also like graded by NN, and in each degree it is like that. Y L some L. And we have L minus EI, and we have more terms. So we can also consider a same sequence but of shifts on Y. So first, I study the local properties of these singularities. We get some nice properties. Like if you want to prove flatness, you want the higher homology of the Kuzu complex to be zero. Then if we have vanishing of higher cohomology, then we get the results here. So we use MMP to find a birational model, Y to Y prime. So depending on L. And we use vanishing theorems on Y prime.
I see. Thank you.
So my question is, so maybe first of all, is there like a similar condition that you can formulate just in terms of the complement instead of the this YD, the model that you have in the main theorem? And maybe the related question is, if I already start with the complement and I look at its LC places, is it possible to see where the condition that you wrote down here, it's somewhat like an open or constructible condition in the given dual complex? I don't know if you have thought about any of this.
Yeah, I haven't thought about the second half. And if I have a complement, and yeah, I thought about like what condition on complement can allow me to construct a model like this, but haven't get some good affirmative result.
Okay, yeah, thanks.
Other questions or comments? If not, thanks again, and thanks all everybody for the presentations.